Right, so I guess this is a good time as ever to start. So just to introduce ourselves then, my name's Mickey. I'm a, third year PhD student now at the University of Bristol in the UK as part of the Bristol Robotics Lab. I myself work on swarms of drones and stuff like that. But for this particular event, I've been one of the sort of leads for developing this game for you guys to try out. With me, we have Professor Jonathan Rossiter, who's going to give a talk in a little bit, and as I said earlier, who will hopefully introduce himself. And we also have Julian, who is on the team of developers making this game. Julian, do you want to introduce yourself?
Yeah, sure. So I'm on the same PhD program as Mickey. I'm also a third year PhD student at the University of Bristol. And yeah, I also work on swarms of robots, so lots of little robots that interact together to do jobs greater than themselves. Yeah, I think that'll be enough of that.
Thanks. Great. So Jonathan, we'll pass over to you then.
I can unmute and then I can hide my bits. Yeah. Right. Do you know, Mickey, if you can see if it is being recorded? If
yes, it's being recorded down at the bottom. Pause and stop recording.
Great. Well, thank you very much. This is just going to be a short intro talk to kind of robotics underground and what robots, I suppose, could do in this kind of environment. And I would like to say, a great thank you to Mickey and Julian and the team for this amazing work that they've done to develop the RocEx robotics program. It's a great demonstrator. I've had to play it. It's very realistic, true to life, I would say. Very, very robot real, we might say. Okay, so my name is Jonathan Rossiter, and I'm Professor of Robotics here at the University of Bristol and Bristol Robotics Laboratory. And I have the pleasure of making robots every day. And that's kind of really exciting because if you're going to be in a field of technology, robotics is one of the cool up and coming areas. And every day is different. So today we're going to look at underground robots. But another day I might be looking at underwater robots or robots that go into the bloodstream and swim around the body. And in all of those cases, those are areas where you want to put robots because you really don't want to put humans. Other examples are in nuclear power stations. If there's a nuclear accident, you really rather use a robot to investigate than you would a human. A human's going to get ill. We've seen that from all sorts of previous incidences. There are places where humans really can't go, in the deepest trenches in the oceans. That's really a hazardous environment for humans to go. And yet we really do want to learn more about what's happening down there. So robots provide the answer, but they need our help. And there are many, many unanswered questions about how robots can be used in those kind of environments. And today we're going to have a look at some of those challenges. So one of the challenges is operating a robot in an underground situation. So if I have a look at one of the great challenges that the American DARPA organization has issued in the last couple of years is a subterranean challenge. And this is, there's a question about how do you explore underground, because it's one of those great untapped resources. Sure, we've been mining for hundreds of years, thousands of years, but there's a lot of resources underground that we haven't got to. We don't want to put humans down there anymore because we know that they can get stuck. And every year we hear of miners who are stuck in these kind of environments. So, it's really not the environment we want to get into, but robots could do it, right? So here's a picture of the Australian CSIRO team from the subterranean challenge run in the last few years. And as you can see, it's a large wheeled robot in this kind of environment. You can see there are sensors at the top around them, and they've got lots of spiky things pointing out on them. And it's really exciting. And clearly with this kind of robot, if you put it underground, it's going to be able to travel through, but it might get stuck. So there are interesting questions about what the shape of these robots should be. But the challenge is in future, how do you put these robots into these environments? Here's another example. This is from the Jet Propulsion Laboratory in NASA, and you can see it's a wheeled robot again with lots of sensors on the top. So you're starting to get a hint as to how sensing the environment is really important, potentially more important than interacting with the environment or moving through the environment. And this one's got very interesting tracks that can lift up and down, so you can kind of go up and down objects and climb over objects. It's reminiscent of the kind of machine you'd put on Mars to explore, right? The kind of rovers, but this is an underground rover. And because of that, you can make it heavier and more interesting. You're not limited also by the cost, which is a real problem with space exploration. So we've got a series of robots that you want to put into an environment underground to explore, to do something useful. And one of the challenges we're going to be having a look at today, and with this game that Mickey and Julian and the rest have put together, is what kind of things you need to put on the robot. What are the challenges that you might face? So I'm just going to quickly overview some of those now. So we can take a little bit of a step back and think about a cavern environment. Is my cartoony cavern environment. And in that environment, there's something that we want to do. Well, maybe we want to explore it, to map it. Or maybe we want to search for something. So just imagine there's some buried treasure. Well, not buried, but some treasure in the cavern. And we have to go and find that treasure. But we are controlling an autonomous robot, or remotely controlling a robot, through teleoperation. And the robot's got to get there. Now, why do we send a robot in there? And as I said before, we want to send a robot because quite often there are scary things in that environment, or things that we don't want to encounter. So we send a robot in. Much rather sacrifice a robot than a human. So there's our robot. Needs to go into that environment, search and find that gold in this case. But of course, along the way, there are many obstacles that it needs to find and to avoid. So it needs the sensors to find them, and then it needs to locomote through them. So what is it going to do? It's going to go through the environment, and maybe first of all, it can see the object in the distance. So it's going to plan a route. Now, of course, it can't just go directly to the object having planned a route, because as it goes, it finds there are obstacles along the ground, along the wall. You might hit his head on a stalagmite or stalactite, if you get it the right way around. But eventually it'll find the gold, in this case, and then it'll bring it back. Okay, one very happy robot. And it's done that because it's interacted with the environment safely, often in the dark, often in the cold. Maybe there is all sorts of chemicals around. There could be chemical gases. So it's got a lot to contend with, and yet it's being able to do that autonomously or with remote control. So let's see if we can make a robot like that, and what we would need. So our little robot here is very characteristic, very caricature. And we're going to take that robot and we're going to put some sensors on it. Now, of course, humans have got lots of sensors. We've got hands, we've got eyes to sense, we've got touch and vision and audio and so on. So the first thing we might do with a robot is to say, let's put human-like sensors onto the robot. So we'd start with the eyes. And so we put a vision system on it. We might just use a camera. But we know that cameras can be more sensitive than human eyes. They can include the sensitivity to infrared, to ultraviolet, to visible light, of course, and also to heat. So those are really attractive qualities that make the robot better than humans. Okay, so that's vision. And at the same time, we can detect sound. We can put microphones onto the side of the robot's head, 2 microphones, maybe one on each side, and we process that information. And in an environment like underground, you might get echoes, you might get multiple sound sources, you might hear some rat scuttling over into the corner, and it's creating all sorts of echoes in the environment. And we could use the sound to locate that object. And you do that by processing the sound signals that come in at potentially different times, and using some relatively complex algorithms, doing some processes like blind source separation, which enables us to combine that information just to generate one direction. Then we can determine when an object is. What's really interesting about that is that we humans are incredibly good at that skill of separating an object from a whole load of different sound signals. You can imagine if you're in a party and then there's 15 conversations going around, you can hone in on one conversation. Robots find that a little bit difficult, but the algorithms are developing fast. So we can do sound, we can do vision. What next? Touch. So imagine if the robot is moving around and it's bumping into things, it would want to find out what it's bumping into. It'll also need to pick up the object, gold, and say, oh yeah, maybe I can't see it, but I can feel that this is a pot of gold. It's heavy. So humans use touch all the time. They use it for lifting objects, for interacting with each other. And our touch is so incredibly sensitive that you can pick up little deformations in surfaces that are down to 50 nanometers. Around 50 nanometers is incredibly small. You can't see it, but you can feel it. So touch is a skill or a sense that the robot really needs, because vision isn't enough and sound isn't enough. So touching an object is needed. So those are 3 human-like senses. one or two more are smell and taste. And you think, why would a robot, if it's going underground, want to smell or taste? Well, smell, I think, is pretty obvious. The robot can smell things that we can't. Well, why? Because smell is a kind of chemical sensing. And there are lots of chemicals underground that you might want to detect. They could be poisonous gases, or they could be some inflammatory gases, right? It could, just before an explosion, the robot could sense that there's some gases coming on, and it doesn't want to move in case it creates a spark. So it immediately shuts down. Taste is one that you don't immediately think of a robot needing, but you can actually have a robot that moves around and licks the floor and detects where chemicals are. And robots have been made like that, and they literally go around and they lick the floor. Why? Because that's another way in which you can sense for chemical deposits, you can sense for organic remains, you can sense for all sorts of things using smell and touch. So it's not obvious, but it's still a very useful sense. One thing that humans can't do, though, that robots can do, is to measure distance. If we wanted to measure distance, we would have to use our eyes, right? Our binocular vision, to be able to look into the distance and estimate that maybe that person is 50 yards away, or that car is 100 yards away, but it's coming towards us. These days, we've got much more sensitive sensors than those for measuring distance. And they are LiDAR and radar and other distance sensors. So you can imagine if you put this distance sensor on the top of the robot and it spins around, you can get some distance information. And if you have a map of that distance information, you've got an understanding of where you are in the environment. So you can use that for localization, for determining where you are, and also for movement so that you can plan where to go. And there are more sensors that you can add on to robots as well. These are more extrasensory, extra-human sensing. So for example, the robot might be able to detect radiation. Humans can't detect radiation except by becoming ill, and it's a little bit too late then. Temperature we can detect, but robots can be far more effective at measuring temperature than we are. But they can measure other things, electric fields and magnetic fields. And so magnetic fields could be very interesting because that might help you to lead to particular kinds of rock formations because the magnetic field is affected by the materials in the rocks. Or electric fields, they could be useful because that tells us something about the materials in the environment or potentially the gases in the environment. So we've got a whole range of sensors that we could put on the robot, and we're just going to look at a few today. But there's one thing I have to say, in that our cartoon robot here is not what all robots look like. There's a whole variety of different robots in the world, right? So we've got robots that look like humans and they behave like humans in the top there. And robots that have got arms and bodies a little bit like humans. And if you were to put clothes on them, they would look very much like humans. Then you've got other robots like these shiny blimps at the bottom. And these shiny blimp balloon objects are still robots. And the drones next to them are still robots, but they are operating in the air. They have different sets of actuators, different sets of motors, different sets of sensors, but they're still robots. And on the right-hand side, we've got a couple of robots there that are slightly different. So on the top right-hand corner there, you can see this robot. I hope you can see my little cursor. This robot is called the EcoBot, and the EcoBot will eat human waste, generate electricity, and then move with the energy that it's got from human waste. And so that's a robot that the researchers at Bristol have made, which eats waste, human waste, right? So from the toilet, but it can move. And that's really exciting because it means that that robot can live in the environment by gaining energy from the environment. And a little bit later, we'll have a look at this other robot here, which has got whiskers coming out of it. And you can see how that hints at other kind of sensors that we might want to use. So let's just assume we can take any of these robots, put them underground. We'll still need to put the sensors on them. So let's look at some of those. So the first one we covered a little bit earlier is vision. Okay, vision is really our primary sense when we're not touching something. Touch is really a much more elemental sense. So if we take vision and we create a robotic system on a robot which has got vision in it, it's going to use a camera. So we take a camera and we take a picture. And then by using some sophisticated algorithms, we do some segmentation, we do some texture analysis, we do some potentially some more distance measurements. Using stereoscopic vision, you end up with a picture like this. And if you squint, you might be able to tell what the object is and what's happening in this scenario. Now, quite often you can't, and it's difficult for a computer to determine what this is. The robot thinks, right, I'm not quite sure what this is. Okay, so what you can do then is to take more photos and manipulate that object with your hand. The robot might move it in its hand. So you have a whole series of photographs, and then you process those photographs to get a kind of decision or an interpretation of what's in the scene. So with this kind of situation where we've got lots of photos, we could then train a system, an artificial intelligence system, to model this kind of environment and to do our seeing and our interpretation for us. So to do that, we might use what's called deep learning. And deep learning is a very hot topic. It's a way of learning from lots of information to produce a very sophisticated result using something like, in this case, a learned neural network. So you can see there's a network there where we take all of this image information, and once it's trained, you put the image information into the network, and we have a conclusion. So the conclusion in this case is that there's a robot hand, I hope you can just see it there, holding a cup or a pot of something, and that tells us what it is, right? So we might keep that, or we might throw it away because, you know, we're underground and we're not interested in cups. Not quite sure why there should be a cup underground, but anyway, it's useful to have this kind of information. So robot vision is a standard kind of sensor which we put on lots of robots, but there are some advantages and disadvantages. So the advantages are that it can be very fast, you know, computation systems can chug and we could do many frames a second, and relatively low cost because you need a camera and a computer. And cameras and computers are ubiquitous because we all carry them around in our pockets via mobile phones. Now, I know some mobile phones are very expensive, but you can get a camera and a computer for $30 or something like that. And that's enough to do this kind of processing. Unfortunately, it's limited on the availability of light. In a completely dark environment, you can see that vision isn't going to work. Or an environment where there's fog or dust in the air, it's not going to work. And on top of that, you need some quite sophisticated AI for this to be really effective. So you need to go through the trouble of training the system, giving it enough information. It could be difficult to get hold of that information because you'd want to get that information from an underground situation first. It's a little bit like this dilemma whereby you want to learn about when nuclear power station, for example, is exploding so that you can train a robot, but you can't go around exploding nuclear power stations in order to generate the data to train the robot. So sometimes this training can be quite challenging. Okay, so that's robot vision. What else? Well, if you have used your vision to get close to an object, then you want to touch it. And we always do this, right? The first thing we do is to touch it. Just imagine that if you're in a room and then somebody switches off the lights at night and it's jet black, right? And you can't remember where the things are in the room. What's the first thing you do? You put your hands out, right? And you use your hands to explore the environment. It's such a primitive sense of touch. So that's what the robot's going to do. If it can't see anything, maybe the first thing it does is to use its hands to touch the walls or to touch the floor and to find out the textures of the walls. So a robot should have fingers and it should have skin. And you can see some examples here. So on the left, we can see a type of sensor called tack tip, which has got a rubber skin on the top. And underneath, there's a camera, which is watching the underneath of the skin. And on the right here, you can see a video, which is showing what happens to that image that we get from the camera as you touch objects onto the top of the skin. And it's very sensitive, this system. It's very soft and very sensitive. And it can even, if you put it on your wrist, it can see your pulse. So you can actually see it on the screen here. So it's a very sophisticated sensory system. You put on a robot, it doesn't cost much because it's just a very tiny webcam and a little bit of rubber, but it's very, very sophisticated. And at the bottom left, you can see some skin that we've made, which enables you to detect where pressure is across the skin. And it does that just by interrogating these 8 electrical connections on the outside. And that blue stuff in the middle of the skin is conductive fluid. It's like a blood, effectively, in the system, but blue blood, right? But that helps us to sense with the skin. Okay, so we've got robot touch, which is with fingers, and fingers are great, but sometimes you don't want to actually touch something. So you use another method. Well, nature is very good at this. And if I show you some videos here, and you can see at the top right, there's a very nice video from Tony Prescott at Sheffield showing what rats do. And you can see rats, when they're interrogating an object or a wall, they move their whiskers. Now, I was so surprised when I saw this video first because I thought rats had whiskers. I knew they had whiskers, but I didn't know they moved them so much. So this rat is moving its whiskers to interrogate the environment. Okay, and even though it's not touching the wall, it can determine that there's a wall there, and it can determine texture and all sorts of characteristics about the wall and whether it should do something with the wall, either jump over it or it should, I don't know, start eating it if it's a different kind of object. And next to that, you can see some of our whiskers that have been developed in the laboratory, which mimic the role of the rat whiskers. So they have artificial muscles at the base, which move the whisker along. When the whisker hits an object, it'll sense it down at the base in the muscles themselves and then send that signal back to the robot. So these whiskers can run in parallel, whole loads of them. They can detect when it hits an object, where it hits the object, and even what kind of object it's hitting. So if you take those whiskers and then you put them on a robot, you end up with a robot a little bit like this. And this is Scratchbot, and it was developed by Martin Pearson and his group. And I think that's his feet there that you can see as he walks around the robot. And you can see that the robot is whisking its whiskers, hitting objects, and it's orientating, it's reorientating just like a rat does. And this robot doesn't just have whiskers that replicate the rat, but it's also got a brain that behaves in the same way as a rat brain. It's got a cerebellum-based system inside, which is behaving in just the way that the rat is orienting when it touches something. And you could see, and it does to me, look like that rat is behaving, the robot rat is behaving just like the real rat. So we've got some touch-based sensors here that we can put on our robot. What are the advantages and disadvantages of them? Well, okay, so touch is great because in a dark room, you don't need any light, right? No light is needed. Processing can be easier if you've got, good algorithms, pretty easy. The whisker doesn't take much processing. The skin is very effective. It doesn't take much processing, but of course there's a limited range because you have to touch an object. Otherwise you can't sense it. And on top of that, it could be fragile. Now, I think we've all put our hands out and cut our fingertips on something, if it's a paper cut or something like that. The same is true for robots. If you're having contact with something, there's a danger that you can break it. And you can see from these whiskers that, if you get it caught in some rock and you pull, you might well break your whisker. So they can be fragile. And the last type of sensor that we might want to explore is the one that I said could go on the top of the robot. And that could be something which is better than humans can do, and that's to sense distance. Now, distance is kind of really useful to combine with vision and touch, because you can use distance sensors to tell us whether you should go towards an object to then use your vision system. And then once you've got your vision system, whether you should go towards an object even closer to use your touch. So it's nice to have those three systems working together: distance for far away, vision if you've got enough light for close up, and then touch for when you're really there. So one distance sensor, which is commonly used in modern systems, and it's used a lot in autonomous cars and in autonomous vehicles, is a LiDAR system. So LiDAR is a little bit like radar, which was used in the past, but radar we don't use because it's too high energy and it's not very healthy around us. But LiDAR is much safer. So LiDAR uses light for light detection and ranging, it's called. So what do? We have emitter, which generates a packet of light. So it's like a glorified LED, a very large shiny LED or a laser, something like that. Sends out a carefully timed packet of light. It's just like basically just a flash. And that travels towards an object. And when it hits that object, it bounces back. Of course, when it bounces back, some of the energy is lost. So the signal is not so strong when it comes back. But when it comes back, it travels back and is picked up by a detector. So you can see in the picture here that there's an emitter, and it's about a distance d, 10 meters to an object, a rock. And you send a packet of light towards that object. And then that object bounces some of that light back again to the detector, and it detects it. Okay, now we still don't know the distance, but we do know the time it took to go from the emitter to the detector. So there's a little graph at the bottom that shows that you've got a pulse of light going out, which is the kind of like the thick red line, and then a pulse of light coming back, which is the detected one, which is the thin red line. And then it took a certain amount of time for that light to travel out and travel back. And if we know the speed of light, c, the speed of light, which is a constant, remember that the speed of light is constant, and then we have t, the time it took, then all we do is multiply those two, divide by 2 because we've gone out and back. Okay, so we need to divide that by 2 to get the distance, and we've got the distance to the object. Now, it has to be said that the speed of light is pretty fast. So this time it takes is actually a very small amount of time, maybe in the orders of nanosecond. So the technology behind this has really advanced in the last few years because the computers that do this kind of processing at this high speed have really become cheaper and more reliable and more effective. So now that we have very small LiDAR sensors that you can buy, sometimes they are only $50 or something like that for the very simple ones, and you can put that on your robot. But of course, a LiDAR sensor just gives you distance in one direction. And if you wanted to find out what the distance of the whole of the scenery was in front of you, you'd have to scan across the whole thing. So that's commonly what happens. You buy a LiDAR sensor that's got this single LiDAR light point that's going out and coming back, and it would measure the distance in one point, but it's continually moving. So it looks a little bit like this. So here in this case, in this blue box, you've got a LiDAR sensor coming down. It's got light coming out, and then the light is reflected back. You spin the mirror. And then the spinner mirror, you can see that that light beam is transmitting all the way around in an arc. And if you keep pulsing light, you get lots of readings. And you can see at the bottom there, these blue readings are coming out. And you can see that an object, in this case, that green cylinder, has been detected because the LiDAR has picked it up. And you can see that the signal just there, okay, there's an object. So you can't see behind the object. Of course you can't, because the LiDAR only goes and hits the object and bounces back. So with LiDAR, we can detect at a distance, and it's very useful, but there are some limitations. So what's good about a LiDAR? It's long range. You can measure tens of meters, maybe up to 100 meters, quite long distance. It's very effective because you don't have to touch any object to get a sense. But unfortunately, it's affected by any kind of reflections in the environment. So if you're trying to use LiDAR to measure objects in a room full of mirrors, it would fall down, because you can just imagine the light would be bounced across all of those mirrors, finally comes back to the sensor and then detector. And then it says, okay, this room is huge because the light took such a long time to get back to the sensor. So it gets very confused. And also, I think you can see at the bottom right there, these points is a limited resolution to the data that you get back, because each time you send this signal out and you get it back again, that takes a certain amount of time. And you can only move at a certain rate for you to get the resolution you want. So either you have lots of samples, you have a few samples and you get those very quickly, so you get a very coarse idea of what's in your room, or you have lots of samples collected slowly, but of course, by the time you've collected the images, all the samples across an image across the space, something might have moved. So there's limited resolution there. So I hope that gives you an idea of the kind of sensors that we put on our robots: distance detectors, vision sensors, touch sensors, radiation, taste, smell, all those exciting things. Okay. And that is what Mickey and the team have put into their cool new RocEx game. Okay, so there's just what the game looks like, but really I'm going to point you to the RocEx game. And now go and play the game. And I'm going to pass you over now to Mickey to go through the game and to tell you what it's like. And that's just a quick introduction to the sensors. Over to you, Mickey. I think you're muted, sir.
Oh, no. After so long and so many video meetings, we still fall in the same traps. Well, thank you very much, Jonathan, for your great presentation. Hopefully that gives everybody a flavor of sort of what sensors are like in the real world. Some of the sensors that we use on our robots all the time. So if you give me a second, and I will put the link to the game in the chat. There we go. Cool. Yeah, so does anybody have any questions for Jonathan? Please feel free to put them in the chat too. While people are thinking up questions, in the next sort of 10 minutes or so, what I'll be doing is I'll be giving basically a sort of a developer's playthrough of the first 5 minutes or so of the game. We'll be talking about some of the decisions we made in making the game, what our aims were, maybe some interesting points. So hopefully that'll be interesting to you. Let's give another minute or so. Any questions or anything? While we're waiting, I'm just going to go share my screen. Cool. Well, if anybody has any questions at any point, please feel free to put them in the chat, and one of us will get around to answering it. Especially now, if you have any questions, yeah, just shove them in the chat, and we can have a bit of a Q&A session afterwards if anyone's got any interesting questions. Cool. So clicking on the link will take you through to our page. So this game is the Farscope entry to the UK RAS Robotics Festival this year. Farscope is the name of the PhD program myself and Julian and a number of the other developers on this game are part of. Farscope stands for Future Autonomous Robotics. I can't remember the rest. So it's all about future autonomous robotic systems, essentially, and doing work in that area. As a cohort, we work on all sorts of different things, from soft robotics, which is Jonathan's area, to drones, swarms, to human-robot interaction, also some of the algorithms and sort of maths behind robotics as well. Cool, anyway, back to the game itself. If anybody has any issues playing the game, please refer to this little page here. We know of some issues. Anyway, so clicking on playing the game will hopefully bring you to the game page itself. It might take a minute to load. If you're on mobile, we hopefully can support you, but you might have to switch browsers a little bit depending. Cool. So in building this game, our aims were basically to introduce to non-robotics people, non-technical people, what sensors are really like. We get the feeling that a lot of people think of robots that they're sort of just they magically know their environment. If you see movies or films, Terminator or whatnot, the robots just sort of know their environment. They know where to go, they know what to do, they know how to make decisions. But we wanted to sort of provide a sort of real life, perspective on the situation with sensors on robots nowadays. So we built this game to do exactly that. Cool. So I'm just going to play through this game. I'm going to sort of mention some comments here and there about certain design decisions and stuff like that. But yeah, so we can start off with just going straight into the game. So with any sort of robotics based game, there are a lot of different ways we can take it. We sort of felt that the cliche ways of doing a robotics game is to stick the robot in Mars or in some futuristic sci-fi landscape. But we really wanted to ground this game in reality, such that you could sort of imagine some researchers or some scientists going out and doing this sort of thing right now. So we came up with this concept of a group of researchers going to explore a cave in the Himalayas, essentially, which is a very real thing. I imagine that there are projects going on now which are doing exactly that. So hopefully this will load. Cool. Awesome. Finish off this. Cool. So our idea for the game was, so you have a lot of games where you're sort of in this weird floating third-person view above the robot, or you have some view of the robot itself. But in reality, you're never going to get a third-person view of the robot. You're not going to have a drone flying behind the robot while you try and control it. This sort of view is actually what it's not quite what you get in reality, but a lot of current day robotics applications, for instance, nuclear inspection, or other areas where people can't go in. This is essentially the sort of view you get. You get a view of maybe your one camera, your two cameras, your multiple cameras. You get a view of, say, your LiDAR system in some way, shape, or form. You might get a map, or you might get something else. But this is essentially it. And we wanted to reproduce this sort of experience where you're controlling this robot, but all you actually see are the sensors. In some ways, this is sort of putting you in the seat of an autonomous robot. These are the raw readings that a robot gets. How should a robot make decisions based on the readings they get? So here we have a couple of different sensors, which we've chosen to include. So we've got the temperature sensors on the left and right. We've got a camera, which we just enabled. We've got the whisker sensor, which is very similar to what Jonathan was just talking about, and we'll look at that in a sec. And we've also got this LiDAR, which we will also look at in a sec. Cool. So before the game comes and tells me to move on, we go and control this robot. So the robot design here, even though you don't see it, is very much reminiscent of those robots you saw in the DARPA Subterranean Challenge. Okay. So we have this whisker sensor on the robot, and you can see the two prongs, as well as a couple of other prongs off the screen. What you'll notice is that when you walk close to things, a bit slippy on this terrain. When you walk close to things, the lights will trigger, meaning that things have triggered the whiskers. Interestingly, I think one of the most sci-fi fictional elements might actually be this whisker sensor. We are very close to having something like this in reality, but this whisker sensor we put into the game is sort of a mishmash of current technologies. So we have the whiskers in terms of the touch sensors, these red and green lights, in terms of what you've touched. But we also have this interesting thing down here, which allows us to classify the material that we've sensed. So right now that's not possible, but we could do that in the future. So if you took something like the TAC tip, which we saw just now, which can, as Jonathan says, has really high resolution in terms of what it can feel. If you move that TAC tip over a texture or over some sort of surface, you get some data about that surface. Then you could put that into some sort of learning system, so like the neural networks that Jonathan mentioned earlier. And with that, you could then classify a certain texture to be a certain sort of material. And we get an effect very similar to this. Cool. So moving onwards, there's a couple of other things I wanted to mention while we're here. So you might have noticed that this camera view is actually rather grainy. It's rather grainy and has a bit of a green tinge to it. So this is reminiscent of essentially showing that when we use robots in the field, there's actually one thing that we haven't talked about so far, and that's communications. So of course we're not dragging a cable to the robot wherever we run it. This robot's running wirelessly, which means we run into communication problems. And something like a camera, it produces a lot of data. So if you imagine this camera here, it's maybe running at 30 frames a second, and each frame has got sort of thousands of pixels. Trying to stream that data along to the user, which is you sitting here controlling this robot, is really intensive. What determines how much data you can send through is known as the bandwidth. And for this sort of application, the bandwidth is sort of quite low, especially considering the fact that you're underground and sort of wireless signals don't propagate very well underground. So you have even less sort of data to send through. So that's why for this particular game, we chose to sort of mimic a lower quality sensor for your lower quality camera for your continuous stream. So that's why you can see it's grainy and other things. But then if you wanted to take a proper picture, we have an option for you to take an actual picture. And you see here, we get a much more high resolution photo. And this is the sort of thing that you'd see. You go in with, say, a lower quality stream, which is perhaps more stable, but it's good enough for navigating. And then you have a higher quality camera on the top of the robot, which you can then sort of collect images of the thing you want to collect images from. Cool, so let's continue with the game. So there's always a question with robotics is like, what do you actually want the robots to do? So in this particular scenario, we found a rock that's unknown to us. So we can take samples of it, and hopefully later on, the robot will keep those samples and we can take them back to the lab and analyze them. And this is very much like the robots, the Curiosity robot, and what's the newest one? Endeavour, I think, or Inspiration, one of those words. The newest robot on Mars too. Cool. So we continue with the story in which story of our game, where this is the second robot you've sent down this cave. The first robot you sent down autonomously because you thought it would be safe, and this is like your backup robot. And the goal for this game is essentially find out what happened to that first robot. So in order to do so, we need to navigate the environment, and this is one of those examples that that Jonathan gave, where right now we're about to go into a tunnel, which is extremely dark. Hopefully you can see that on your screens through the stream. So now we go and turn on the light up. And we see an image very similar to what was on Jonathan's presentation. We see this periodic refreshing, which is essentially because the LiDAR we've got stuck on the front has that rotating mirror. And here we're just showing the raw data, essentially, from the LiDAR itself. We're not doing any processing. So we get a dot when we actually sort of hit something, and then we refresh the page afterwards. So here we see we have walls on the left, right, and something over there. But there's a difficulty. So right now I'm moving, but the LiDAR also turns as I move. So you actually get a distorted image. But that's one of the challenges in this game of using the LiDAR itself. How do you navigate with the LiDAR sensor? So here I go in, it's completely dark. I have no idea where I am. I have some torches on the front, but as you can see, they're not very useful. So we go forward. Maybe there's an exit somewhere up here. Go forward again. And it looks very odd. We don't see anything else. Maybe there's a rock or something, but it's just a dead end. So we turn around and we see if there's a way out. And essentially you have to look very carefully, because if you're not careful, you can quite easily just turn around and go back the same way. But this is one of the challenges of this particular little bit, is there is actually a fork just to the left in this darkness, which you can only make out with the LiDAR itself. And this is where you just have to throw yourself into the darkness and just hope that you're going the right way. And in this case, we can see we're still moving forward. So I think we found the way out. So yeah, so we continue moving down the tunnel. We can essentially just use the LiDAR for navigation. And this is essentially what a robot running autonomously would have to do. I have to identify both sides and basically just try and drive down it and work out where to go next. Oh, it's interesting. We can hear some water in the background. I wonder what that's implying. Go forward. And we've made our way through to a cavern. With a nice waterfall in it. Cool. I'm going to take a picture there. Commemorate the time. Yeah, so a couple of other features maybe to show. So missions, we show the missions up here. That helps sort of categorize what we want to do. And in fact, if you're to do this in real life, you'd follow a very similar form where you go to a certain place and you have a certain job to do, and you've got to like follow that. because it's a team of people at the end of the day who are working with you to complete the mission. Other useful things include the journal, keeping a track of where you've been, things that have been said. That's always really useful. And if you want to refer to any of this information, we've put a useful sense page down here with some interesting things and some more pictures of the TAC tip. So this is a particular version of the whiskers, which was put on a robotic arm. And it was used for, I believe, localization of objects and sort of working out what shape objects are. And here's another TAC tip. Cool. So this ends the sort of the walkthrough that I'm going to do for the game. I highly recommend now that you just go and play the game for yourself, experience it. Let us know how it was for you. Hopefully it was good fun. Cool. So I'm going to quit to the main menu. Cool. Yeah. So that brings us to the end of sort of the tutorial walkthrough, I guess. Does anybody have any questions for us before we end the session? Yeah, so thanks for your comment. The LiDAR was a really interesting one, actually, because there are some people who absolutely struggle with using it. If you have a good sense of spatial awareness, if you can sort of navigate around your house in the dark, or if you don't get lost when you go navigate the streets of Bristol or London or whatever, then I think that has a good correlation with being good at using the LiDAR. But I have a couple of friends who have no sense of direction. And they really struggle to begin with to get through that little dark area that I just took you through. So I think it shows the difficulty sometimes in relying on raw data and the sort of difficulties and problems that roboticists have to solve to make that data usable, especially to an autonomous robot, let alone to a sort of a human. Cool. Any final comments or anything like that? Oh, Jonathan.
Well, I was playing the game along there, and it's very realistic. It is absolutely like being the robot, which is not often we get a chance to be like the robot. And I found that was fascinating, and also getting the audio as well, which is it's doing it now. I get these
I've still got it going on.
And it's very, very cool. Very, very realistic. Really good.
Well, if that's all, I guess thank you all very much for coming along. Hopefully this has been insightful and interesting. And I hope you guys enjoy the rest of the Robotics Festival. Please go play the game. Awesome. Thank you very much.